Welcome to the deep dive. It's great to have you with us today.
Yeah, really glad to be here.
If you're the kind of person who, loves that sudden aha moment and really thrives on looking at the world from multiple, sometimes completely competing perspectives, you are absolutely in the right place today.
You really are.
Because our mission today is to dig into this incredibly fascinating, highly technical deep dive. We're looking at a blog post from a Japanese creator who goes by the handle Xionod2023.
Right, dated March 10th, 2026.
Exactly. And the sources we're pulling from include this wild mix of translated AI interactions, deep dialogues with models like Gemini, Claude, and ChatGPT right alongside these incredibly detailed geometrical diagrams.
It's a remarkably ambitious thought experiment, honestly.
It really is. The hook here, the whole mission of this deep dive is that we are going to explore a visually stunning alternative to our Einstein's theory of special relativity.
This is huge.
Yeah. We'll examine a concept called the Spherical Cap Model. And the core argument here is that to keep the speed of light constant, we don't actually need to stretch or dilate time.
At all.
Right. Okay, let's unpack this. Because to understand why someone would even try to reinvent relativity, we have to look back at the foundational problem that started all of this, the famous Michelson-Morley experiment.
Right, let's set the stage. Back in 1887, the Michelson-Morley experiment, or the experiment, tried to detect the Earth's movement through space.
Through the ether, basically.
Exactly, the lumiferous ether. They did this by measuring the speed of light in different directions. The expectation was that if the Earth is moving, light traveling in the direction of that movement should be affected.
It should take a slightly different amount of time than light traveling perfectly perpendicular to it.
Precisely.
And Xionod2023 breaks this down using some very specific math generated in a dialogue with the Gemini AI. Imagine you have this interferometer. It has these 10-meter arms, and it's moving at about 1/10,000th the speed of light.
Which is roughly the Earth's orbital speed.
Right, so the AI calculated that the light traveling along the axis of movement, the one going with the Earth, should arrive slightly later than the light bouncing perpendicularly.
And the numbers the AI highlights here are microscopic but crucial. The calculation shows an expected delay of 3.33 times 10 to the negative 16 seconds, 333 attoseconds.
333 attoseconds.
Yeah, and to translate that into what they were actually looking for in 1887, they were looking at interference patterns, or fringes. That 333 attosecond delay equals a shift of about 0.2 fringes.
And here is the absolute historical mind-bender for you. Back in 1887, their equipment was actually precise enough to detect a shift as small as 0.01 fringes.
It was incredibly sensitive for the time.
So a 0.2 fringe shift should have been glaringly obvious to them. It should have been right there on the table. But they saw nothing.
Nothing at all.
Zero shift. The light arrived at the exact same time.
And to put that in a modern context, modern equipment can detect variations down to 10 to the negative 18. So this 10 to the negative 8 discrepancy is massive. It would be instantly detected today.
It's an elephant in the room.
Exactly. And Einstein solved this null result by proposing that time itself dilates and space physically contracts, Lorentz contraction. He did this specifically to preserve a flat 1D spatial line.
Right, to keep the grid flat.
What's fascinating here is how Xionod2023 approaches this exact same problem. What if Einstein's foundational assumption of a flat Cartesian absolute space is the actual illusion?
Oh, this is where the blog post really gets going. To explain how we perceive reality, the source introduces these three distinct layers of observation, and they use this really helpful tennis court analogy.
It makes the math so much easier to visualize.
It really does. So let's look at observer 1, the local player. This observer is moving at a very high speed, say 0.6 times the speed of light, straight along the x-axis with their equipment.
They're the ones on the court.
Right. They are in the thick of it, experiencing the local world. Just like a tennis player who only sees themselves, their racket, and the ball right in front of them.
Then we step back to observer 2, who the text calls the calculator. Now, this observer is entirely stationary in Maxwell's electromagnetic field. Think of them as a spectator sitting perfectly still in the stands.
Just watching the match.
Exactly. But because they are stationary and observing from a distance, they receive light from different points on that x-axis at different times. This is basic information delay. Delta t equals distance divided by the speed of light.
Because the far side of the tennis court is further away, the light takes slightly longer to reach their eyes.
Yes, but observer 2 doesn't see a warped tennis court. They use their memory to mentally compensate for that lag. They artificially stitch that delayed information together to create a flat x-axis in their mind.
That is such a key takeaway. The flat plane we think we see is an illusion. It is a calculated reconstruction of past events patched together to look like now.
Which sets us up perfectly for observer 3.
The higher dimensional describer, the umpire.
Right.
So imagine the umpire sitting in the tall chair, high above the tennis court. According to the source, observer 3 is positioned at a complex mathematical depth. Let's say at a z-axis coordinate of 1,000.
High above the 2D plane.
Yeah. And to this umpire, the word simultaneous has a very strict definition. It strictly means equal past.
Meaning the information took the exact same time to reach them.
Exactly. If two things happen simultaneously, the light from both events must have traveled the exact same distance to hit the umpire's eyes at the exact same moment.
But this creates a profound geometrical dilemma. If observer 3 demands an equal past for all points on a flat Cartesian plane, the math simply fails.
It breaks.
It breaks entirely. A flat plane cannot satisfy an equal distance from a single elevated point. The points right under the umpire's chair are physically closer than the baselines of the court.
Right.
So to maintain this strict equal past where all information arrives having traveled the same distance, that one-dimensional flat space must curve.
It has to literally bow upwards into a dome so the edges are closer to the umpire. And that brings us directly into the core theory, the spherical cap model.
This is Chat's alternative to Einstein's time dilation.
Here's where it gets really interesting.
Instead of time dilating or stretching out to make the math work, reality is described on a curved, two-dimensional spherical cap situated in complex space.
So the flat 1D x-axis we think we live on it's just a projection.
Merely a projection.
Yeah.
Information delay, the fact that light takes time to travel, is translated physically into geometric curvature.
Let's break down the specific mathematical parameters they provide for this. Because to keep a constant distance, that equal past degree they call r, the model uses an imaginary axis.
Represented by E tau.
Right, I tau. And it uses this imaginary axis to absorb the time delay. The math states r squared equals x squared plus h squared minus tau squared.
And they run the numbers to prove it. If the height, or h, of the observer is 100, the radius r is approximately 141.42.
Which gives a very specific curvature of about 0.00000007.
Exactly. The time delay is completely absorbed by the spatial geometry of this imaginary axis.
Okay, but how does this relate to Lorentz contraction? Because the whole idea is that moving objects physically shrink as they approach the speed of light. That's a huge part of standard physics.
Well, according to the spherical cap model, matter isn't shrinking at all.
At all?
Not at all. The source gives this brilliant visual. A moving object is actually tracing a constant geodesic arc along the sloped, curved surface of this complex dimension.
It's moving along the dome.
Right. What we observe is contraction. What we think of the object getting smaller is just the flat horizontal projection. It is literally a shadow cast onto our flat Cartesian x-axis.
That is wild. The object is normal size up on the curved dome, but because we only see the flat shadow on the ground beneath it, it looks shorter to us.
Exactly. It's an illusion of perspective. And this perfectly summarizes the beauty of this model. That missing 333 attosecond delay from the Michelson-Morley experiment, it doesn't exist.
Because the physical delay in the direction of travel
is perfectly canceled out by the geometric path difference on the complex curved surface. The light converges geometrically on exactly one point.
The geometry solves the null result without ever having to touch the concept of time.
Exactly.
I know that is a lot of heavy geometry we just walked through. You might be listening and thinking, okay, this is a neat math trick, but why does it matter? So what does this all mean?
It matters because it challenges our most fundamental assumption. The assumption that we live on a flat, pre-existing Cartesian grid. It suggests that objective reality isn't a single shared stage.
Like we're all just walking around on the same flat board.
Right. Instead, observers build their own geometry based on the arrival of information and the integration of their own memory.
That is a huge philosophical shift.
It really is. If we connect this to the bigger picture, whether you are firmly on Team Einstein or you're leaning towards Zionad 2023, just having this alternative framework represents a Copernican shift in how we model simultaneity.
It offers a purely spatial geometric solution.
Exactly, rather than a time manipulation solution. It proves that the same physical observations can be explained by a completely different underlying architecture.
Which brings up my absolute favorite part of the source material, the meta-experiment. The author actually polled AI models, like Claude, on these two competing theories.
Oh, this was fascinating.
Before reading the spherical cap materials, the AI heavily favored the Einstein perspective. It gave standard relativity a 90% support rating, and Zionachat only got 5%.
Which is expected. The AI is trained on basically every physics textbook ever written.
Right, it's just repeating the consensus. But after processing this new geometric model, after evaluating the imaginary axis and the curved shadow concept, Einstein's support dropped by 15 to 20 points.
And the Zion-Chat model gained 10 points.
Just from looking at the math. Even the AI found this higher dimensional logic persuasive. It realized the math actually worked perfectly to solve the 1887 problem without breaking time.
It's incredible.
Let's pull back and wrap this up, because this has been quite the journey. We went from a 19th century light experiment with a missing 333 attosecond discrepancy up into an umpire's view of the universe.
Looking down from z equals 1,000.
Right. And finally, we came to the realization that our entire reality might just be a flat shadow cast by a curved, complex sphere.
And this reinforces the true value of deep dives like this. Knowledge isn't just about accepting the established facts. It's about looking at the exact same data, like that Michelson-Morley null result, and realizing there might be an entirely different mathematical architecture hiding in the background.
The data doesn't change, but the map we use to read it does.
This raises an important question.
It certainly does, and it's a thought I want to leave you with today. If the very fabric of space and the physical size of objects are just flat shadows cast by a higher dimensional curvature of time and information, what other solid, supposedly unchangeable facts in your daily life are actually just flat projections of a much more complex, hidden reality?
It really makes you rethink everything.
It really does. Thank you so much for joining us on this deep dive. Keep questioning your perspective, and we will see you next time.